Hello, everyone. Welcome to Chapter 3, Section 7. This is Rates of Change in Natural Science. And basically, what this is going to take some of the basic rules of derivatives that you've already learned and show you some applications with them. Okay? So, for engineers, a lot of applications end up being in physics, and we've already talked about velocity and acceleration and their relation to distance. So notice S equals f of t, that's the position function. That's our distance function of an object moving in a straight line. Now, when we take the derivative of the distance, that's when we end up with velocity. And then when we take a derivative of the velocity, which is the second derivative of the distance, that's when we end up with acceleration. So, let's look at an example with this. Notice example 1 here. It says, the position of a particle in motion is given by this position function here, okay? Where S of t is measured in meters and t is measured in seconds. And so we have been asked to find the velocity, okay? Find the velocity at time t. So if we're asked to find the velocity, that is just simply us taking our derivative. So notice, first and foremost, we have the derivative of 4t cubed, and so that's going to give us 12t squared. Then we have a derivative of negative 9t squared. So 2 times negative 9 gives me a negative 18. And when I subtract 1 from the exponent, I just get t to the first. And then the derivative of 6t, derivative of anything to the first power, remember, is always the coefficient. And then the derivative of 2 would be 0. So what you're looking at now would be our velocity function with respect to time. Now, once we have that velocity, we can actually, that velocity function, I should say, we can actually figure out what our velocities are with respect to time. So notice, what is the velocity after 2 seconds? So in other words, what I'm being asked here is what is v of 2? And so we're going to take our 2 and we're going to plug it in everywhere we see a t in our velocity function. And when you punch that out right in your calculator, it should give you 18. Now listen, folks, always remember your units. So up here at the top, S of t, remember, is in meters, t is in seconds. So with velocity, it's distance over time, so that's going to be meters per second. Okay, meters per second. All right. Then, notice what this asks us. When is the particle at rest? So I need you to think about this. When a particle is at rest, that means our velocity is at 0. We're not moving. Okay? So we need to figure out where in relation to this particle of motion is our velocity equal to 0. So we need to take our velocity function here and we need to set it equal to 0. Now the good news about this particular velocity function, it doesn't work that way on all of them, but this particular one has a GCF. 6 can be divided out of all of these, just leaving you with a 2t squared minus 3t plus 1 equals 0. Now, based on what you have left, you have a quadratic equation. So, of course, you could factor it. You could use your quadratic formula. You could use complete the square. Any of these things to solve it. This one does factor pretty easily, okay? So I'm going to use factoring. Notice we know because this is a plus sign that our signs are the same. And since this is a minus sign, we know they're both going to be subtraction signs. There's only 2 factors of 2t, and that's 2t, and t. And then there's only one set of factors for 1. 1 times 1. So notice we have our factors pretty easily there. Now, take 2t minus 1, set it equal to 0, and t minus 1 and set it equal to 0. Now notice what we have. We get a t to be 1/2 when we solve that equation, and we get t to be 1 when we solve this equation. Now, this is t, this is time, so this represents seconds, right? Seconds. So when our time is at 1/2 seconds, our particle is at rest. When our time is at 1 second, our particle is also at rest. Okay? So it's a matter of setting your velocity equal to 0. Alright? Now, I mistyped this myself. Letter E should have come before letter D. So let's look at letter E first. Letter E says this. It says, when is the particle moving in a positive direction? Okay? When is the particle moving in a positive direction? So this particular word here, moving, that lets you know that we're talking about velocity here. So we want to know when the velocity is going to be positive. So we need to know when 12t squared minus 18t plus 6 is greater than 0. Now, once we divide them all by 6 again, we end up with our same quadratic inequality. And it factors in the same exact way. So 2t minus 1 times t minus 1 is greater than or equal to 0. Now remember, with quadratic inequalities, we need to test intervals, okay? So look, I'm going to put 1/2 and 1 as my two critical numbers here, because if I solve this, I get my t to be 1/2, and if I solve this, I get my t to be 1, just like we did right up here, okay? So it's the same exact thing. So look at this. We need to test this, okay? So pick a number less than 1/2. So I'm going to pick 0. All right, and I want you to plug 0 back in these two spots for t and see what you get. Well, if I plug 0 in for t here, I get -1 times -1, which is a positive 1. Well, positive 1 is greater than 0. So I know below 1/2, I'm going to be moving in a positive direction. All right, pick a number between 1/2 and 1. 0.75 is between 1/2 and 1. Test it in these two. Now, when you plug 0.75 in here, you're going in for t in both of these and punch it out in your calculator. You're going to get a negative number. So obviously a negative number is not greater than 0. So we know the velocity is negative here. All right, and then pick a number bigger than 1. So I'm going to pick 2. Well, 2 times 2 is 4, minus 1 is 3. So the first one is positive, and 2 minus 1 is positive. So a positive times a positive is going to be positive here. So when we plug 2 back in here, we get another positive answer. So we know we're moving in a positive direction in that interval. So basically, this is what we know. We know for a fact that when t is less than 1/2 and when t is greater than 1, that we're moving in a positive direction. Okay? Now, based on that, and based on knowing when it's at rest, we can actually figure out letter D. So letter D asks you to find the distance traveled in the first 3 seconds. Okay? Find the distance traveled within the first 3 seconds. So what we can do is we can break our interval up into the resting periods. And here's what I mean. Look, we know we start our t at 0 seconds. Time starts at 0 seconds. And we go to 1/2. 1/2 is our first rest period. Okay? Then we go from 1/2 to 1. Now I'm getting this 1/2 and 1 from right up here, my rest periods. And then we go from 1 to 3. Now how did I know I needed to stop at 3? Right here in my problem, okay? So I've got these 3 periods that kind of divide up my how my object is traveling, okay? So I need to figure out the distance here, okay? And so the way we're going to figure out the distance is like this. We're going to take each of our times, and we need to find the distance covered in each of these time intervals here, okay? So here's how we're going to do that. So for our first interval, we're going to do the absolute value of f of 1/2 minus f of 0. F of 1/2 minus f of 0 gives us the distance between 0 and 1/2. Now, does anybody know why do I need the absolute value bars there? Because think about it. When I'm going in a positive direction, this number is going to be positive. But when I go in a negative direction, this number is going to be negative. But even though I'm going in a negative direction, it's still a positive distance. So think about it. Distance is always a positive number. So that our distance here is always positive, we need those absolute values there. Okay? Just to be sure. So when you take 1/2, and it's not f of 1/2. In this case, it's going to be s of 1/2 because our function up at the top is in terms of s here. So s of 1/2. So I'm going to take 1/2 and I'm going to plug it in everywhere I see a t in this problem, and I'm going to punch it out. And so when I do that, s of 1/2 is going to be 3.25 minus. Then take 0, plug it in up here into our distance, our position formula. When we plug 0 in for t, we get 2. So when I subtract here, I get the absolute value of 1.25, which gives me a distance of 1.25 meters. Now, I knew that it was meters because of the problem up here. The S of t is measured in meters. Okay? So that's our distance we covered in a positive direction. We know it's positive because this number in here came out to be positive. This is our distance in a positive direction, okay, for this interval. Now we need to do the same thing for the other 2 intervals. So we have s of 1 minus s of 1/2. Now the good news is we already know what s of 1/2 is. It's 3.25. We solved that for the last problem. We just have to figure out what s of 1 is. So take your 1, plug it back in to your position function up here, and punch it out. See what you get. Now, s of 1, if you punch it out correctly, is going to be 3. So that gives us a negative 0.25. So the absolute value of negative 0.25 is 0.25. So this is 0.25 meters. Now, what should be important for you to note here is notice how this number in here is negative. So that means instead of going forward in the positive direction, we went backwards in the negative direction of 0.25 meters. Okay? Then solve our last interval. Okay, so we're going to do the absolute value of s of 3 minus s of 1. And for this particular problem, we already know what s of 1 is. It's 3. So we just have to figure out what s of 3 is. And s of 3 comes out to be 47. So that comes out to be 44 meters for us in a positive direction, notice. Now, notice what it asked, okay? Each of these represents the distance traveled in each of these individual meters. The problem asks, find the total distance in the first 3 seconds. Okay, so to find our total distance here, we need to take, so our total distance, we need to add together all our distances here. So 1.25 plus 0.25 plus 44 gives us 45.5 meters for that particular problem. So in this problem, we traveled 45.5 meters. Now, some of it was forward in the positive direction, some of it was backwards in the negative direction. But all together, we covered 45.5 meters, okay? Hopefully that's understandable. If not, please let me know and ask a question on that, okay? Now look at letter F. Letter F says, can you draw an illustration of what the particle is doing here? Well, think about it. Okay. If we were to draw this based on position, okay, we could have it like this. Okay, so this represents our position. And so at time 0, when t equals 0, we're at the 3 meter mark. At the 2 meter mark. So this is t equals 0. Now, when you go for 1/2 second, we're now at 1.25. But notice, we're at rest. And then we come back 0.25 and are at rest again at t equals 1. And then we come back and we go all the way out here to the 45 and a half meters. So notice, this is kind of what we're doing. We're going forward, then we rest, backwards a little bit, rest again, and then forwards the rest of the way. So that's kind of what our particle looks like here. Now, we knew we started at 2 because when t equals 0, when we plug 0 in for all this, we get 2. And we figured that out up here when we did s of 0. Okay? So that's what it means when it's drawing the particle. Okay? Drawing the motion. All right, so let's look at another example. And this one says a ball is thrown vertically up in the air, upward, with a velocity of 80 feet per second. The height after t seconds is given by h of t equals 80t minus 16t squared. What is the maximum height of the ball? So think about this. If I throw a ball up in the air, at some point, I didn't want it to be a straight line, but at some point, that ball gets to the highest point up here in midair, and for that split second it's at its highest point, it stops. It's not moving, and then all of a sudden it starts to come back down. This point right here, where it stops, like I said, it stops for a split second. That means at that moment, your velocity is equal to 0 at that very moment. Okay? So what we need to do, you're not going forwards or backwards, you're stopped. So what we need to do, in order to find the maximum height, we need to figure out where the velocity equals 0. Because where it equals 0 right here is going to be where our ball stops at maximum height. So watch what I'm going to do here. My velocity is going to be my derivative of my position function here. So that's going to be 80 minus 32t when I take the derivative of my function there. Now, what we want to know is, where is the velocity equal to 0? Because wherever it's equal to 0, that is where our ball stops for that split second in the air before coming back down, which would be the maximum height. So this is 80 equals 32t, or 80 over 32 equals t, which 80 over 32 is 2.5. So that's 2.5 seconds. Okay, so after 2.5 seconds of going up, it stops, then it comes back down. But we didn't want to know the time. We wanted to know the height. But notice how our height here is a function of time. So when we know the time that it stops at that height, we can take the time, plug it back in for the time up here, and be able to figure what the height is at this moment. Okay? So watch. So I'm going to figure out what h of 2.5 is. So that's 80 times 2.5 minus 16 times 2.5 squared. And when I punch it out, that's 100. Now, notice it said feet up here. So that's not meters, that's 100 feet. So that is the maximum height of the ball after we have thrown it up in the air. Hopefully that makes sense. When the velocity is 0. And the velocity is 0 because it gets to that point where it stops for that split second before it starts coming back down. Okay? Alright. So let's look at another physics. It could be physics/biology example. Okay? And this is our last example here. But a physics/biology example. And listen, there are infinite number of examples. I couldn't give you one of every type just simply because, like I said, there are infinite numbers. But I'm trying to give you some common ones, okay, so that you can apply these to your homework, all right? It's the same kind of process in solving those. So if you look at this, notice what it says. It says a stone is dropped into a still pond, creating a ripple that travels outward at a speed of 40 centimeters per second. Okay? Find the rate at which the area within the circle is increasing after 3 seconds. All right, so think about this. They've asked you to find the rate. That's how we know that we're looking for a derivative. We want to find the rate after 3 seconds. So what they've actually asked you to find A prime. Now, how did I know it was A prime? Because we're looking for the area of the circle. Now, an area of the circle, area is pi r squared in a circle. Now, we need to figure out, though, because we are in centimeters per second. So we're dealing with time here. So we don't have any time in our problem. So how can we relate this to time? Well, look. Our radius here is expanding at 40 centimeters per second. So, that being the case, at 1 second, every second, our radius is expanding 40 centimeters. So we can say that the radius here is going to be 40t, because however many seconds we have, that's how many 40s our radius has already expanded. So we can take 40t and replace our r with the 40t. Now we have this in terms of time, because notice, we have to have it in terms of time to be able to find our final answer, because we would need to know what is A prime of 3 seconds. Okay? So at this point, Now we can take the derivative. Okay? So, well, before we take the derivative, let's simplify this a little bit. So, 40 squared is 1600, and t squared is t squared. So this is really 1600 pi times pi t squared. Now that we've done that, let's take the derivative, now that we've simplified a little bit. So if we're taking the derivative here, notice these two are constants. So just like we do with a normal derivative, when we take a derivative of t squared, we're going to take the 2 and multiply it times our constant. So that's 3200 pi times t to the first. Because remember, we subtract 1 from the exponent. So this right here represents our rate formula. So we want to know what the rate is, how much it's increasing after 3 seconds. So we want to know what is a prime of 3. Well, that's 3200 pi times 3, which in this case is going to be 9600 pi. But now you got to remember your units. We know since it's a rate, we know it's per second. They gave us that in the problem. But here's where people tend to make a mistake. They see this centimeters up here, and they want to write centimeters there. That's the velocity. Area is distance squared. So the way the area is increasing is square centimeters per second. And so we would be increasing at a rate of 9600 pi centimeters squared per second after 3 seconds here. Okay, that's the rate at which our area is increasing. Okay, so on some of these problems, you're going to have to remember some of your geometric area formulas and things like that. Okay, so there's not too many problems on this homework set, so give it a try. And if you have questions, come by and see me. I will gladly help you any way I can. So let me know if you need it. It's been great talking to you this evening.